2026 is the 100th anniversary of Schrödinger's equation. This elegant equation expresses the conservation of energy for quantum particles, connecting the classical equation for wave oscillation to de Broglie's formula relating particle wavelengths to their momentum. To celebrate this milestone, I'm dedicating 2 full videos to go through these equations in all their beautiful detail. Today's episode will dig into the mathematics of wave equations in the context of classical physics problems like vibrating strings. The next episode will apply these concepts to achieve a deeper understanding of Schrödinger's equation and the quantum mechanics of atomic orbitals. Welcome to Atomic Universe. I'm Dan Bergstrom, materials scientist. Our plan for today is to start with the equations for the basic oscillation of a mass on a spring, show how these equations can be extended to describe traveling waves, look at how traveling waves combine to form standing waves like those on a vibrating string, and then discuss the solutions for standing wave vibrations in higher dimensions. The equations describing these different types of oscillations were largely worked out by Swiss and French mathematicians of the 18th century. Names like Daniel Bernoulli, Leonhard Euler, Joseph Louis Lagrange, and Pierre-Simon Laplace. If you're comfortable with all the second-order differential equations shown here and their solutions, congratulations! Feel free to skip this video and go to the next one. If not, don't be scared off. Understanding them is as easy as riding a swing, or in our case, a spring. In this classic physics problem, a spring hanging from the ceiling supports a small weight of mass m. Now, in real life, the mass will bob up and down on the spring until damping converts all of the kinetic energy to heat and brings the mass to a rest at a point where the force on the spring balances the force of gravity. Let's define the variable u to represent displacement from this balanced location, with positive values of u for upward displacement and negative values for downward displacement. U equals 0 is the place where the force of the spring is equal to the force of gravity. To make this problem simpler to analyze, let's forget about the real world and use what's called an ideal spring. We will pretend this spring doesn't have any damping effects, and the restorative force of the spring is given by a simple linear relationship called Hooke's law, where the spring pulls back with a force in exact proportion to the amount it stretched. So the force F equals negative k times u, where k is called the spring constant. Using Newton's law of F equals ma, this tells us that the force of minus ku will equal mass times acceleration. Now to solve this equation of motion, we're going to have to use a little calculus, but I promise it'll only be a little. The bit of calculus we need here involves derivatives. A derivative is a rate of change. In this example, the velocity of our mass on the spring will be given by the rate of change of the displacement per unit time. For an infinitesimally small amount of elapsed time, dt, we can write the change of position as du, so our velocity equation is given in calculus as du divided by dt. This is called taking the derivative of u with respect to t. Similarly, we can say the acceleration is the rate of change of velocity per unit time, or in terms of calculus, the acceleration is simply the second derivative of our displacement u with respect to time, which can be written as d squared u divided by dt squared. So putting all this together gives us an equation of motion where negative k times u equals mass times the second derivative of u with respect to time. Now we just need to figure out a function for our displacement u in terms of time that satisfies this condition. Looking at our plot from before, a good guess would be to try u equals cosine of t. So let's plug that in and see what happens. Well, what happens is we need to take the second derivative of the cosine function. Let's do this in 2 steps. To better visualize the first derivative, take a look at the slope of tangent lines on each point on the cosine curve. The slope can be calculated as rise over run, where here the rise is our small change in u, du, and the run is our small change in t, dt. We can plot the value of this slope versus time using a little video magic, where we construct similar right triangles and scale the base to equal 1 at each time t, so that the height will be just the derivative we're looking for, du over dt. Using those triangles, we can then trace out the full derivative curve as shown here. Or you could just memorize the calculus tables and recall that the derivative of the cosine function is given by minus 1 times the sine function. To get the second derivative, we just repeat this procedure, or just look up the derivative of the sine function is the cosine function. Either way, we find the second derivative of the cosine function is just -1 times that same cosine function. Well, this is great, because when we plug it into our equation of motion, the cosines cancel out. Unfortunately, when we do this, we see our equation will only hold true when k is equal to m, which would be an amazing coincidence. But we're clearly on the right track here, so let's see if we can find a more generic cosine function for u versus time. There are three standard constants we can add to our cosine function for fine-tuning. Multiplying the whole cosine function by an amplitude factor a will make it oscillate between a and negative a instead of 1 and negative 1. Inside the cosine function, multiplying time by an angular frequency factor called omega will increase the rate of oscillation and decrease the wavelength to a value of 2 pi divided by omega. Finally, adding a phase shift term phi inside the cosine function will shift the wave horizontally along the time axis. Now if we go back to recalculate our derivatives for this new function, we see that the slope of the cosine curve increases with amplitude factor a, so our derivative function needs the same factor. The cosine curve and the derivative curve will oscillate with the same frequency, so our derivative needs the same factor of omega inside the sine function, but at any given point on the wave, the slope is also increasing with omega, so we'll need to add another factor of omega outside the sine function next to a. Finally, the phase shift of the cosine and derivative functions need to match, but the slope isn't otherwise affected by a phase shift, so we just need to add the matching phi inside the sine function. This gives us that the first derivative of u with respect to t is negative a times omega times the sine of omega t plus phi. By a similar argument, the second derivative will just add another factor of omega outside, giving negative a times omega squared times the cosine of omega t plus phi. Plugging these into our equation of motion, the cosines cancel as before, but the extra omega squared stays, giving us the condition that omega must equal the square root of our spring constant k divided by mass. So there you have it. All we have to do is make sure our cosine wave has the right frequency factor for the strength of our spring and the weight of the mass, and presto, we have a valid equation of motion. Since a and phi are not constrained, our mass will oscillate with the same frequency no matter how far we stretch the spring to start with, and no matter what time t we choose to release it. By the way, the equations for a swinging pendulum work out to be very similar to those for oscillations on a spring. The trick here is that since the displacement occurs along a fixed radius, it's better to switch to polar coordinates so that our displacement function u becomes r times theta. The downward force on this pendulum is mass times the gravitational constant. Decomposing this force into our polar coordinate components gives a radial component of mg cosine theta that gets balanced by the tension in the string holding the mass, and a tangent component of mg sine theta that accelerates our mass back towards zero displacement. So let's use Newton's law of F equals ma to calculate acceleration in the tangent direction. The m's cancel, giving negative g sine theta equals acceleration. As before, the acceleration is our second derivative of the displacement with respect to time, which is now r times the second derivative of theta. For small angles of swing, this force curve is quite nearly linear, with the sine of theta being pretty close to the value of theta itself as measured in radians. And so our swinging pendulum equation becomes very much like an ideal spring obeying Hooke's law. The generic cosine function works as a solution again, and we get the condition that our angular frequency needs to be the square root of the gravitational constant divided by the radius of our pendulum arm. At large angles of swing, these equations will break down due to the nonlinearity of the force curve. So if you want a more accurate clock, you want one with a long pendulum arm and a small angle of swing, like a grandfather clock or Big Ben. Let's now go up one level of complexity and consider a chain of masses connected by springs in a line along the x-axis which are stretched to a tension force T. If we start moving the first mass perpendicular to the x-axis, we will generate waves which travel down the chain to the right. Again, we need to make some simplifying assumptions to make the situation easier to analyze. These masses are on a frictionless plane so that the waves can travel undampened. We will assume the mass of these ideal springs is negligible compared to the masses themselves, and we'll assume the vertical displacements of the masses are all small compared to the distance between the masses. This way the tension won't change too much, and we can use small angle approximations as we did in the example of the swing. Let's start by looking at the physics of this situation. Again, we will want to apply Newton's law of F equals ma to say the force is equal to mass times the second derivative of the vertical displacement with respect to time, but first we need to figure out what are the forces acting on each mass. Zooming in on one mass, let's call it the mass at position x sub n. The displacement u will be a function both of this position and of time. We'll call the distance between the masses delta x, and the displacements of the two neighboring masses will be measured relative to the central mass as delta u minus and delta u plus, respectively. We see that the springs attached on either side of this mass put it in a tug of war between the force exerted by each spring. Let's call the force from the mass at the n-1 location F minus and the other one F plus. Now let's decompose these forces into their horizontal and vertical components Fx and Fy. Since we are constraining ourselves to small displacements, we can assume the horizontal forces are just given by the spring tension T. These horizontal forces thus cancel out, leaving only the vertical forces to calculate. Due to the forces being directed along the lines connecting the masses, we can use geometry to say the ratio of each Fy to each Fx will be the same as the ratio of each delta u to each delta x. Thus, Fy equals the tension times delta u over delta x, and the net force in the vertical direction will be T times the difference in the delta u's over the delta x's. Now by definition, the slope of the displacement curve is delta u over delta x, so we can think of the term in parentheses as the rate of change of the slope per distance delta x. The slope is just the first derivative of the displacement function, and the rate of change of this derivative is just the second derivative. So the difference between the adjacent slopes, a distance delta x apart, will just be the second derivative of u with respect to x times delta x. One caveat here is that we are assuming the delta x is small with respect to the difference in the slopes. But now we can plug this equation for the net force into Newton's law and see that T times the second derivative of u with respect to x times delta x must equal m times the second derivative of u with respect to time. Or we can rewrite that as the second derivative of u with respect to time equals tension times delta x over mass times the second derivative of u with respect to x. Okay, so now we need to find a displacement function u, which is a function of x and t, that solves this condition. Let's start by freezing time and noticing that our wave looks a lot like a cosine function again. So we can reuse our equation from the single mass on a spring with amplitude, frequency, and phase shift constants, but this time we plot the curve versus x instead of t to make a stationary wave. Now we need to figure out how to make this wave move with time. Recall the effect of changing the phase shift constant phi was to shift the wave laterally, so we can turn our equation into a traveling wave by making this phase shift a function of time. For a wave moving at constant velocity, it should be obvious the phase shift function will just be a constant times t. Note that as the phase shift increases, the wave will move towards the negative direction on the x-axis. So if we want a wave moving to the right, we should set our phase shift function to minus c times t, where c is some positive constant. Plugging this in, we see that every 2 pi over c seconds, our traveling wave will move one full cycle of phase shift. The distance of travel here is one wavelength, which is given by 2 pi over omega. Thus we can say that our wave must travel with a velocity which is the distance of one wavelength divided by the time it takes to move one wavelength over. The 2 pi's cancel, leaving our wave velocity v as equal to c over omega. Solving for c gives omega times velocity. Thus, we can rewrite our equation of motion as u equals a times the sine of omega x minus omega vt. To see if this equation works in our differential equation, we need to calculate those second derivatives. We'll do this by taking the derivatives of u with respect to t at a fixed location x, and then taking the derivatives with respect to x at a fixed point in time. The idea of taking derivatives with respect to one variable while holding the other constant is a common thing to do in math and physics, and it's called a partial derivative. The notation for this is to replace the d's with curly d's to make it clear we're taking derivatives with respect to one variable while holding the others constant. If we treat x as constant, omega x gives a constant phase shift to the cosine of negative v omega t. This allows the same kind of solution we had for the single mass hanging on a spring. And indeed, at any given location x, our wave function will move up and down just like our mass on a spring did. The only difference is that each derivative brings out an additional factor of v in addition to omega. So the second derivative of u with respect to t will be negative omega squared v squared times the original displacement function. Next, if we freeze time, we can calculate the second partial derivative of u with respect to x as simply negative omega squared u. To merge these two equations into one, we can regroup the first equation so that we can more easily plug in the second one to give the final differential equation for a traveling wave as the second partial derivative of u with respect to time is equal to the velocity squared times the second partial derivative of u with respect to x. Thus, our equation of motion is a valid solution for the original differential equation provided that v equals the square root of the spring tension times delta x divided by the mass. Now we can make a few additional observations here. Note that in this example there's no constraint on the frequency, so any period of oscillation can be used to launch our waves. Next, we haven't really used the spring-like nature of the springs in this analysis. The masses could have been linked together with strings and the equations would be the same. In fact, if we define the Greek letter mu to be the mass divided by delta x, then we can make that delta x arbitrarily small until our system is transformed from masses connected by springs to a continuous string with linear mass density mu. So now it's time to add another layer of complexity to our system and see how two traveling waves can interact. We'll start with our cosine displacement function for a traveling wave and have it collide with a displacement wave of identical frequency but traveling in the other direction with negative amplitude and velocity. You can see graphically that these two produce a standing wave. Mathematically, if we expand the displacement functions using the cosine addition and subtraction identities, and then add the waves together, the cosine terms will cancel, and we get a wave function which is the product of two sine functions. The first of these functions is a stationary wave which depends only on the position, and the second of these depends only on time, like our mass on a spring solution. These two functions multiplied together then result in a standing wave whose amplitude oscillates with time. One application of this standing wave equation is to describe the vibration frequencies of stringed instruments. A vibrating string has the constraint applied to the equation that there is no vibration at the start and end of the string. That is to say, the displacement u at these locations must be 0 for all times t. Since the second sine function will not be 0 for most values of t, let's focus on the positions x where the first sine term will be 0. X equals 0 works, so the displacement will always be 0 at the left end of our string, and also the sine function will be 0 for any location where x times omega is a multiple of pi. This means that for a string of length L, we can have allowed vibration frequencies where omega is equal to n times pi over L, where n can equal any integer. N equals 1 is called the fundamental frequency of the string, and n greater than 1 gives the overtones. In addition to the endpoints of the string, there are going to be n minus 1 locations along the string where there is also 0 displacement at all times. These are called the nodes of the vibration. It is also interesting to look at what happens if we join the ends of our string together to make a vibrating loop. Where the ends join, we'll require that the string must be continuous and not kinked. So not only does the displacement u need to be matched at x equals 0 and x equals L, the derivative of u with respect to x must also match at both ends of the string. These constraints are only met for lengths L, which are whole numbers of wavelengths. So let's pick a new integer variable m, which is n over 2, so that we can replace n times pi with m times 2 pi. This means that omega is now m times 2 pi over L, cutting the number of possible frequencies in half. It also makes sense now to move our displacement to polar coordinates, so we'll make the substitution that theta equals 2 pi radians times x divided by the length of the string. Finally, to make the equations more elegant, we can define the variables alpha sub n and alpha sub m to be n times pi over L and m times 2 pi over L respectively. You can think of alpha as the frequency of the vibration nodes as you go along the string. In addition to looking cleaner, this change of notation will allow us to reuse these equations in the next section, where it will be easier to understand the math by analogy with these two equations than by going through the details of the algebra. One final note on these equations for vibrating strings and vibrating loops. Because n and m in these equations must be an integer, we will say that these vibration equations are quantized in the variables n and m, to be more in keeping with the language of quantum mechanics. As we increase the degrees of freedom in the next section, we'll need both n and m as independent quantum numbers to describe the vibration. Staying with the musical world, let's increase the complexity of our problem one more time by considering two-dimensional standing waves on a drum head. The displacement u will be a function of the location x, y and time t. The physics of this situation is similar to that of a vibrating string, but with the added complexity of the second dimension. So the wave equation has second derivatives for u with respect to both the x and y directions, as well as time. The combination of second derivatives in x and y is called the two-dimensional Laplacian operator, after the French mathematician Pierre-Simon Laplace, who studied such equations. Assuming we have a circular drumhead, it will be convenient to rewrite this equation into polar coordinates, which following Laplace has three terms, two involving the partial derivatives of u with respect to r, and a second derivative with respect to the angle theta. To analyze this equation, first let's consider the case for a fixed radius r. The first two terms go to 0, so this equation reduces to the case for a standing wave vibration, which we have just solved. So for any circular strip, the vibrating drum will look very much like the standing wave on a loop of string. Now let's look at the equation at a fixed angle theta. Here we have a second derivative of r plus a 1 over r times the first derivative in r. Considering the case where the radius r is very large, the first derivative term will be very small, and this equation again reduces to our standing wave equation with just the second derivative term. But for smaller r, this term will add significantly to the acceleration of the drumhead as given by the second derivative of u with respect to t. So, for a slice of the drum along the diameter, we should expect something that looks like a sine wave solution, but different in that it needs a stronger acceleration of the vibration in the center of the drum. The exact solution for this type of equation is a Bessel function, named after the German mathematician Friedrich Bessel. What we need here is actually the Bessel function of the first type, which is known as the well-behaved Bessel function, lucky for us. We'll call this function j sub m, and its value is given by an integral of nested cosine and sine functions as shown here. While this integral cannot be solved analytically, I can plot it for you. As you see, there are separate Bessel functions for different quantized modes m, and each one looks sinusoidal for large radii, but the vibrations get more intense in the center, exactly what we're looking for to describe our radial drum vibration. So it turns out the final displacement equation we need to solve our equation of motion is just the product of the amplitude factor a times the sine m theta term from the loop vibration equation, times the Bessel function term from the radial vibration equation, times the sine lambda vt term that is common to both vibration modes. Thus, we can think of drum vibrations as simply combining the vibration modes quantized in the radial direction by n and in the circular direction by m. The constraint of zero vibration on the drum circumference leads to alpha sub m and sub n values, which are quantized as before, except now they need to be calculated from the zeros of the Bessel function. Here are the animated plots for this final equation for the first few modes of m and n. The simplest vibration mode is m equals 0, n equals 1. As we increase m and n, we see increasingly intricate vibration patterns. These standing vibrations also have nodes where there's no displacement, but it's hard to see them in these three-dimensional plots. We can highlight them by making a contour plot of the average displacement distance. One way to do this, which will be useful later for interpreting the real Schrödinger equation, is to plot the average of u squared over time so that both the negative and positive displacements contribute equally to the peaks of the plot, and the nodes where there is zero vibration can be easily seen. With all this background and wave function math out of the way, we're finally ready to increase the complexity one more time and look at those three-dimensional wave vibrations like Schrödinger's equation for electron waves vibrating in an atom. But we're going to leave that for the next episode. Before we wrap up today, however, I would like to show you an experiment you can do yourself to make the two-dimensional vibration modes we've been studying easily visible with what are called Chladni patterns. These are named after German physicist and musician Ernst Chladni, who had the idea to put sand on a drumhead, or as shown here, a vibrating plate suspended like a cymbal from a central point. When the vibration starts, the sand will naturally move to the nodes of zero vibration, making them easily visible. As you can see, higher frequency vibrations create more densely packed nodes of zero vibration, just as we calculated and plotted. Beautiful. That's it for today. Thanks for watching.